Yeah, my goal is to talk about one conjecture of Dubrovin, Liu, Yang, and Zhang. Yeah, it's still open; it's not proved, and yeah, and I will talk about the classification problem that they proposed, and about two conjectural solutions to it. One was suggested by these authors, and another one yeah, was suggested in yeah, my works with co-authors. Yes, okay. So, and the starting point of is the KdV equation and its remarkable properties. So yeah, so okay, of course, yes, everybody knows a lot about KdV, but I will describe the properties that are important for me. So we consider the KdV equation, which I write in this form. Yes, and then it has a lot of properties, and one of them, in particular, the following one. It has the KdV equation has an infinite number of commuting flows, which can be written in this form. Yes, and yeah, in particular, the KdV equation itself can be written in the right-hand side of it is dx of some polynomial. So and yeah, when and for me, so probably I will sometimes say integrable system. For me, integrability means just the existence of an infinite number of commuting flows. So the first point is integrability for me, and then yeah, these flows, higher flows of the KdV equation, have this form. So this Pn. Yeah, the initial term is this one, w to the power n plus 1, and plus some polynomial in w's and its derivatives.
To say that degree is less or equal than n.
Yeah, I mean, one can yeah, as a result, yes, but yeah, I can avoid this restriction, so I can just say that this is a polynomial. So this one is a polynomial, yeah, arbitrary polynomial in wx, yeah, and high derivatives that do not contain this monomial. Yeah, so they contain all possible other monomials.
Okay.
Yeah. Yes, and it's very yeah. Yeah, yes, again, everybody knows that. Yeah, it's a very strong restriction. So all these, if you fix these initial terms, then actually the commutativity of the flows uniquely fixes all the rest. Okay. Yeah, and also, I mean, if we consider commuting flows where the right-hand side is a polynomial in w and its derivatives, then actually these flows give a basis in the space of all commuting flows of the KdV equation. Okay. Yeah, then the KdV equation is a Hamiltonian. So yeah, this property means that higher flows are Hamiltonian. That higher flows are Hamiltonian. Yeah, where you know, I guess I recall the definition of the variational derivative. where I also denote W with lower index n is dx power n of W. Okay. Yes, and then also these flows satisfy this additional condition that if we differentiate Pn by W, then we get Pn minus 1, and if we want it to be true for n equals 1, then we should set that P0 is W. Okay, so and the whole so this is these are the properties of the KdV equation that are important for me. Then the whole system of flows, this system of flows together with the first one is called the KdV hierarchy. Okay, and then one can ask a natural question: are there other equations with the same properties? Where I mean, where to be precise, I mean that so that all these three properties, this one, and this one, are satisfied, meaning that the initial terms are exactly like this. They are Hamiltonian, and we have this property. In particular, the first equation should also start from WWX plus higher terms. It looks like there are no other equations like that. The literature about integrable systems is huge, so probably it can be easily deduced from some results, but I did not see a proof of it. But okay, so it looks like there are no equations with the same property up to obvious rescalings. Of course, I mean we can we can make some rescalings to change actually these coefficients here, and in particular we can there is a limit, the so-called Hopf equation, where we can get rid of this term, and then all higher terms in all other flows will also disappear. Okay, of course, and this I mean that looks like there are no other equations like that up to obvious rescalings. Okay, and then if you want to get something interesting, we have to relax some conditions, and there is a huge literature about that. A lot of complete results and a lot of open problems and conjectures. And okay, I just would like to mention a couple of them. People considered the classification problem of PDEs of this form, for example, of this form, where the highest term is WXXX like KdV, and where the lowest terms can be a rational function. And then there's a classification of integrable PDEs of this form, where a certain unique role in this classification is played by famous Cauchy-Vernovnikov equation. Okay, and then there is other classification problem that I would like to mention is one can consider integrable PDEs. And again, by integrability, I mean the existence of an infinite number of commuting flows of this form. So we can say that the right-hand side is a polynomial where the highest term is Wn plus some polynomial in W and its derivatives up to n minus 1 derivative, where we require that probably so that the whole right-hand side is homogeneous. That this right-hand side is what people called lambda homogeneous polynomial. That if we assign to Wi degree I plus lambda for some positive lambda, then the right-hand side is is homogeneous. Yeah, there is then there is a result of Santer's Wang about classification of such PDEs. Okay, and I would like to speak to talk about more recent conjecture of Dubrow and Liu Yang Zhang, relatively recent conjecture, which gives a relation with a very interesting algebraic geometry and topology. So a rich theory comes up if we just relax the condition of polynomiality. So in the when we consider the KDE equation, we said that the deformation, so we said that the right hand side is Wn plus 1 plus some polynomial. But we can say that, okay, we can, I will say precisely, but yeah, roughly speaking, we can say that the right hand side is now a formal power series. Okay, and then what do I mean precisely? Yeah, so I would like to introduce, there is a standard notion of differential polynomials. So differential polynomials are yes, so yeah, there are two versions. One can speak about just this thing. So we can, sorry, it should be polynomial. So it's a polynomial in the derivatives of W, starting from the first derivative. Yeah. And with the coefficients that are formal power series in W. So in particular, we can consider. So we would like to consider some elements like this. And and also one can consider formal power series in epsilon with coefficients that are differential polynomials. And this is also called a differential polynomial, the space of differential polynomials. Then one introduce grading by this formula. So the degree of Wn is n, and degree of epsilon is -1. So it's a different grading from the one that we considered for lambda homogeneous polynomials. So so it's a standard differential grading. Okay, and then we would like to consider partial differential equations of this form. Of this form, where the right hand side is dx of some differential polynomial of degree 0. So and this means that the right hand side is dx of, and then I write the first few terms. So some formal power series a plus epsilon, some formal power series times wx plus epsilon square, and so on. We say that the differential degree is 0. Which means that epsilon comes to the power, which is to the power that is equal to the number of derivatives appearing in the coefficient of this epsilon. So basically epsilon just is introduced just for convenience. We just want to say that the right hand side is some infinite linear combination of differential polynomials of different degrees, and just epsilon controls the number of x derivatives that appear in the terms. And then if one did not see this before, then one can think that this is something too abstract, probably not appearing in nature, but no, some actually equations like in the example below, like this intermediate long wave equation. So actually various equations can be after some algebraic manipulations can be written in this form. Can be written in the form where some differential polynomials with the infinite tails appear. Yeah, and then my favorite example is the intermediate long wave equation, which describes waves on water surface in certain regime. And yeah, so using this formalism, yeah, it can be written as in this way, where this W, where B to G are Bernoulli numbers. Bernoulli numbers. Yes, and then yeah, and then probably in this way ILW doesn't appear very often. More frequently, it appears in this form. In this form, yeah. So one knows that B to G Bernoulli numbers appear as coefficients in the decomposition of the hyperbolic cotangents. Okay, then this is written here. Actually, yeah, and then moreover, when actually one actually if you want to speak how it appears in nature, yeah, intermediate long wave describes water waves in certain regime, and actually originally from physics it comes as some integral equation. But after some, I mean, this form can be obtained after some algebraic manipulations. Okay. Yes, and then and then just a general remark that in principle, this infinite series. So I mean, some discrete equations after again some manipulations can be written in this form. Using the fact that if W is some function of x, then the shift of W can be written as epsilon exponent epsilon dx W Wx. So some epsilon Wn. So so which shows that actually using differential polynomials we can also access some some semi-discrete equations of a certain type, where the right-hand side of equations are is some discrete equation. Meaning where the right-hand side depends on values of our function W at some points on some lattice. Okay, this is just to say that differential polynomials are not so frightening. They are quite natural. Okay, and then I can formulate the problem that Liu, Yang, and Zhang considered, and obtain some and propose some interesting conjecture. So I mean, basically, I require the same thing. Yeah. So maybe again I can return to So for KDE, so we require the initial term. We required the initial term looks like this. yeah, that the right hand side is yeah, variation derivative of some polynomial. Yeah, and then this equation. Okay, and then I mean we just say the same, but we just say that all the rest is a differential polynomial. Yes. So yeah, this is the problem. Yeah, so we want to consider such systems. Yeah, where the right hand side is a differential polynomial of degree 0, where the initial term is like this, such that the flows pairwise commute. Okay, I mean, yeah, okay, I said a local functional, but actually, yeah. So I mean, it's not necessary, which I can just say for some differential polynomial, for some differential polynomial. HM. Yeah, and then this property, yeah, that the derivative by W gives us the previous equation. But now we, since we now allow differential polynomials, we obtain a large group of symmetries. And namely, there is a large group of transformations that can act on PDEs of the form that we can consider, and they are so-called Miura transformations. Yeah, and by Miura transformation, I mean transformations that look like this. So when we make a change of variables from W to W tilde, that starts from W and then some correction. Yeah, so which is a differential polynomial of degree 0. Yeah, then here I write several terms. Where again this A, B, and C formal power series. Yes. So yeah, I mean, yeah, these yeah, we have to consider such transformations. Yeah, and of course, I mean, working with them is quite yeah, it's quite complicated. Yeah, so if one tries to, for example, given some simple formula like this, some change of variables, yeah, even computing its inverse. Computing its inverse is can rarely be done explicitly. Okay, I mean, one can compute up to some terms and up to some powers in epsilon, but yeah, obtaining general expressions, explicit expressions, usually quite complicated. Is usually quite complicated. Yeah. So yeah, and then yeah, similarly, yeah. If we have some system of PDEs, then making a Murat, if one wants to make a Murat transformation, then okay, I mean, one can compute after some powers of epsilon, but yeah, I mean, it's doable, but yeah, usually yeah, explicit computations in all of the whole expression up to any order of epsilon is can be quite complicated. Even yeah, so maybe I have to also say that one of the motivations for introducing some transformations, yeah, in the classical theory, make some motivating remark. Motivation is that, yeah, in the classical theory, changes of variables of the form W goes to W tilde X equals F W plus some polynomial plus some polynomial in W, Wx appear. In particular, there is a famous Mura transformation that maps solutions of modified KdV equation to KdV to solutions of the KdV equation. So there is change of variables that maps solutions of mKdV to solutions of KdV. But such transformations do not form a group. Do not form a group. So if one tries to invert this thing, then one gets infinite expressions like this. Okay, this is motivation for one of the motivations to introduce these Mura transformations. And then De Broglie, Liu, Yang, and Zhang proposed this problem. Try to find such systems up to Mura transformations that preserve these properties. Of course, this property that the right hand side. So in particular, we get that the right hand side is dx delta Hn delta W. This property can be not true after an arbitrary Mura transformation, but one can still the space of Mura transformations that preserve these properties is still very large. It's infinite dimensional. Okay, and then so this is a problem. And then I would like to speak about conjectural solutions, which involve algebraic geometry, particularly the modular space of curves. Maybe at this point there are any questions?
For me, it's okay.
Okay. Okay, if there are no questions, then I will go to the modular space of curves. So I would like to speak about conjectural solutions from the modular space of curves. From the modular spaces of curves. So there are two approaches. Yes, and so for this, we consider the modular space of curves. So MGN. So we have we fix GN, greater non-negative numbers, and then this modular space of curves is, as I said, it's the set of isomorphism classes. Isomorphism classes of algebraic curves or of marked nodal Riemann surfaces. Mark nodal Riemann surfaces. Just to draw a picture, so we consider Riemann surfaces with marked points, but we also allow nodal singularities. So and we can also have some number of points. And then okay, so just to draw what can happen, we can have something, some self intersection. Yeah, and then we have marked points x1, x2, x3. Yeah, okay, and then here we have x4, x5, x6. So points of this modular space are isomorphism classes of curves, and then we require that xi's of curves C. So xi belong to the smooth part of C. C smooth. Yeah, and we also say that all these singularities are nodal singularities, meaning that locally xy equals 0 in C2. They are smooth. Yeah, and then okay, the genius of the curve is G, and then we require that the automorphism group is finite of C. So this is yeah, so this is the classical object in algebraic geometry. Yes. So yeah, so of marked curves, yeah, and I didn't say that. Yeah, marked. So n marked points, n marked points. Yeah, so this is this space. Yeah, so M03 is a point. Yeah, and okay, M04 is CP1. Yeah, and in general, M0n as a natural structure for complex manifold is a complex manifold. Compact. Yeah, and MGN is almost like that. Is almost like that.
So MGN bar is probably Deligne-Mumford compactification.
Yeah, yeah.
So you have to compact.
Yes. So, yeah, but I mean, that's why I say that we allow singularities.
Okay.
Yeah, yeah. Allowing singularities. Yeah, yeah, they compactified this modular spatial smooth Riemann surfaces. So yeah, so it's also called yeah, Deligne-Mumford. Yeah, Deligne-Mumford. So Deligne-Mumford, they considered this set and introduced a natural complex structure on it, and proved some basic properties of this space. Yeah, and yeah, MGN is almost like a complex manifold. I mean, it's an orbifold, but in many aspects, it's very close to manifold. Dimension, complex dimension is 3G minus 3 plus n. Okay, yeah, then there are natural, yeah, then if we have some fixed Riemann surface, then one can assign to it some objects, and then when we vary Riemann surface in this modular space, then we get some family of some objects over the modular space. Yeah, in particular, if we have some curve, and we have we can consider the ith mark point xi, and we can assign consider the cotangent. So we have so a Riemann surface. We have cotangent spaces to the ith mark point. And then if we vary this in a family, then this gives a line bundle Li over the modular space MGM. Yeah, then one can introduce the first. One can consider the first Chern classes of these line bundles from the second cohomology group of MGN bar. Yes. Yes, and then also, given a Riemann surface, one can assign to it the space of holomorphic differentials. Space of holomorphic differentials. It's G-dimensional. Dimension equals G. And then this gives rank G. Vector bundle. The so-called Hodge vector bundle E over MGN. Yes. And this was already introduced long time ago by Dring Mumford, and they actually tried to describe the cohomology groups of at least of this modular space and or modular space of smooth curves using these basic classes. But then it occurred that it's very big and this class is not enough. But okay. These are the most natural cohomology classes that one can introduce on these modular spaces. Yes, and then there is one more class that I would like to consider. So we can consider integers. And with the vanishing sum. And one can consider the following very natural object. One can consider smooth. So C. We consider one can consider smooth curves of genius G with n marked points. X1, Xn, smooth, such that the divisor sum AI xi is a principal divisor. Is a principal divisor. So and then one can consider the closure of it. So as a result, this is some actually some also classical variety in MGN. But we would like to consider the dual cohomology class. Dual cohomology class. And this is the so-called double verification cycle. Yeah, I mean, okay. Actually, one has to also okay, it's some approximate definition. One can has to correct it a little bit, but I don't want to in the details. Okay, one can imagine this this picture, yeah, and this gives some cohomology class of degree 2g on MGN. Yes, and then yes, and then I have to also introduce. So these are basic classes, yeah, classical classes, cohomology class on the modular space of curves. Okay, and then to be honest, yeah, I don't have yet too much time, so. Yeah, so people then, yeah, philosophically, one has to consider here rank 1 cohomologic field theory. So, I mean, okay. So then one we would like to consider. We consider. We consider. Yeah, rank 1. Rank 1 cohomological field theory. Cohomological field theories on MGN. And actually, yeah, what I would like to tell you works, I mean, in any rank. But I mean, here, since since I would like to relate what I would like to say with with this conjecture, with this Dubrovin and Liu Yang-Zhang problem. For this particular cohomologic field, so I can give a definition, of course, of rank 1 cohomologic field theories, but it's easier, but they are all classified. So it's easier not to give a definition, but just to say the answer of the classification. So instead of defining, instead of defining, it was this notion was introduced by Konstantin Manin. So instead of defining them, so I just explicitly describe all of them. Explicitly describe all of them. Yeah, and then I mean, this is actually, I mean, this was a famous result by Telemans. So it's Telemans' result. Who, yeah, starting from the definition that I don't want to say, prove that they all can be described in the way that I would like now to present. Yeah, and then yeah, what is this description? We just fix a sequence of numbers S1, S2, and so on, S3, some complex numbers, and then would like to consider the following family of cohomology classes. Family of cohomology classes on MGN. So for each GNN, we would like to consider a cohomology class CGN, which is just the exponent of the sum I greater or equal to 1 S I, the Chern character, the Chern, the 2i's minus 2I minus 1 Chern character of the Hodge bundle. Yeah, so this is a Chern character. Chern character. Yeah, some characteristic class. Yeah, why odd ones?
What is E? Chern character of what?
E is a Hodge bundle. This bundle of holomorphic differentials. Yeah, so this yeah, this bundle of holomorphic differentials. Yes, and then why odd ones? So here, yeah, there's a classical result by I guess also Mumford that the even ones are 0. Okay, and then we consider we can consider this class, and then one can do the following. One can consider. Yeah, then one can. There's a construction of a system of a system of PDEs. Okay, and then yeah, I can explicitly construct it using these cohomology classes. So what we do, we consider the double replication cycle. Double replication cycle. Corresponding to n+1 mark points, so minus a1 minus an, a1 an. So the sum should be 0. So I would like to the last n. I mean, the first one can be expressed in terms of the others. Okay, and then I would like to consider psi 1 to some power d, and then would like to consider the top class of the Hodge bundle. Yes, and multiply by our cohomological field theory, CGN. This is what I called cohomological field theory. Cohomological field theory. Okay, so one can consider this family of cohomology classes on MGN plus 1, and one can take the value n+1. Yes. So yeah, strictly speaking, this this class is not homogeneous. Yeah, because it's exponent of some classes mixed in mixed degree. Okay, now and we just take in this whole expression, we take the part of degree equal to the dimension of this space, yeah, and then take the value on the fundamental class. So we get some expression that depends on these numbers a1, an. And then there is yeah, a result of yeah, some probably one should refer to it as a Heinz result. That this is a polynomial in A1 AN of degree 2G, so homogeneous of degree 2G. So yeah, probably I should say that it refer to it as a Heinz result. Yes, it's more general, but I mean it's a standard consequence. And then okay, one can take the coefficient. So this is a polynomial. One can take the coefficient of a1 to the power d1, an to the power dn in this polynomial. So as a result, this is some number. Okay? And here now we sum overall choices. So we take G, we define G, D. We take the sum overall choices that we made, epsilon power 2G factorial. And here we sum overall D1, Dn. Sum of di's is equal to 2G. Yes, and then we take this coefficient, yeah, and multiply it by W d1, W dn, d2, W dn. So we take yeah, monomial in the derivatives, in W in its derivatives. Yeah, recall it by W k, I mean dxk of W. Yeah, so yeah, so this is what I would like to take. This is some differential polynomial. Yeah. Differential polynomial. Yes, and then yes, and then this is there is this theorem. So it's there is a theorem saying that the system the flows dw d tn equals dx variational derivative w and oh maybe d should d is a system of I mean the flows are pairwise commute. Pairwise commute. Pairwise commute. And have the form from this the problem, the Brogden-Liu-Yang problem. Yes. And then yeah, then we have a conjecture that for each I mean, for each Muir equivalence class in this de Broglie-Liu-Yang problem, I mean, these, I mean, and then the conjecture is that these systems give exactly representatives in all in Muir equivalence classes of the de Broglie-Liu-Yang-Zhang conjecture. So then there is conjecture. Conjecture, which we proposed together with Dubrovin, Gere Rossi. It says that these systems give representatives in all Miura equivalence classes, in the de Broglie-Liu-Yang-Zhang problem. Yeah, so meaning in this problem, yeah, so one considers Miura equivalence classes, and then the conjecture is that in each Miura equivalence class there is a system like that, and any two systems like that are not Miura equivalent. Yeah. So they exactly parameterize all orbits under these Miura transformations.
Is the second part known, that these are not Miura equivalent?
Formally, yeah, I think formally it is not written. It is not written, although I think it's not hard to prove. But yeah, it's not done. It's not in principle. Yeah, it's a nice problem. Yeah, I think it's not hard, but yeah, it's not done. Okay. Yes, and okay, I have yeah, how much time? Oh, it's my time is over.
It's okay. So as you like.
Okay, maybe I make one more remark. More remark that, I mean, because yeah, I did not yeah, say what I actually announced, because I said conjectural solutions. Yeah. Because I mean, actually, de Broglie-Liu-Yang-Zhang, they proposed another way to construct the systems. So yeah, and then so you see that we constructed these systems, and we see that we explicitly constructed equations. Yeah, by a very explicit formula, this one. But actually, yeah, before this conjecture, before de Broglie-Liu-Yang-Zhang proposed a parallel conjecture. A parallel conjecture constructing I mean, integrable systems starting from a solution. starting from a solution. So, okay, I can just say very briefly. So one can. So how to do that? One has to consider the generating series of so-called intersection numbers with the cohomological field theory. So one considers the following formal power series, which is the sum of all choices, epsilon to the power 2g over n factorial. And here we do a similar thing. We sum over all d1 dn. And but here we just take the integral over mgn psi1 to the power d1, psi n to the power dn. Yeah, just take these numbers and multiply by td1, tdn. Yes, and then there is a result that there is a unique system of PDEs of the form that we like, dtd equals dx PD of the form such that w equals second derivative of f dt0 squared is a solution, is its solution. Yeah. There is this result. So saying that starting from a very natural formal power series, one can construct a system of PDEs such that this second derivative is solution, where we as usual here in the story people identify T0 with X. Yeah, and then actually, yeah. So and actually, they have a parallel conjecture, Dubrow-Liu-Yang-Zhang conjecture, says that these systems give representatives. I mean, these systems give representatives for the Muir equivalence classes. Yeah. Yes. So this was the original conjecture. So there are two approaches for constructing representatives, and they're different. So one representative has a very natural solution, but the equations, I mean, one can write some explicit formula for them, but what's a formula, but it will be not nice. But other approach for giving representatives for the Muir equivalence classes here gives explicitly the equations, but solution again. In our works we wrote some special solution, but again it's not nice. So in one approach we get a representative with very clear equations. In other approach we get a system representative with a very clear. Actually, these systems are Muir equivalent, And yeah, these are all conjectures. Maybe just one more remark. I mean, this system, just to give some names, this is called Dubrovnik hierarchy, Dubrovnik hierarchy, or hierarchy of topological type. And this system that I introduced, it's called a DR hierarchy, because it's the DR cycle is involved in it, so DR hierarchy. Okay, so then, I think at this point, I finish. Thank you very much.
Okay, thank you very much. Are there any questions?
Yeah, may I ask a question?
Surely.
How do you get KDV along this line?
KDV is obtained from for KDV, we just choose CGN, just the unit in cohomology in H0 MGN. I mean, it corresponds to the choice of our parameters SI equals 0. And then both actually DR hierarchy and Dubrovnik hierarchy are equal, and they are KDV, exactly KDV hierarchy. And then I mean, maybe just to since you ask, maybe other example. So other example is when the CGN is equal to the full chart class of the Hodge bundle, so plus C1 CG of the Hodge bundle, and then DR hierarchy is exactly ILW hierarchy, and DZ hierarchy is a Muir equivalent. For this one, Muir equivalence appears, some Muir equivalence. Yeah.
Do you know examples there for which both construction do not coincide?
Yeah, typically they don't coincide. So I mean, it's not proved, but typically, I mean, for almost all cohomological theories. Okay. Since I speak, I mean, this construction works in for cohomological theories of higher rank. But if we speak about, I mean, this rank 1 cohomological theories, I think KDV is the only example. This trivial cohomological theory, I mean, this one is the only example where these two hierarchies coincide. In all other, for all other values of parameters, a Muir transformation. I mean, there is a Muir transformation between them. Conjectural. I mean, it's not proved, but.
Sasha, I'm sorry, I missed, maybe I missed the role of the cohomological field theory in the construction of BZ hierarchy. Of the
did I?
Generating function, which
I didn't include it. Oh, this is very bad. Sorry. Of course, thank you very much. Of course, I mean, I mean, of course, thank you very much. So we integrate classes of our cohomological field theory and arbitrary monomial psi classes.
Is it natural to think about some duality of such of both constructions, or it is not clear?
I like to say that it's kind of duality, because on one side we have geometrically nice solution, but geometrically bad equations, and on the other side we have geometrically bad solution but geometrically good equations. But I mean, I can't say anything more clever than that regarding the duality.
Are there any ways to think about this construction in terms of I don't know, Grassmannian, Sata-Grassmannian, or something like this, something algebraic from the integrable point of view, so from the integrable side?
Yeah, yeah, yeah. Probably one can. It's natural to expect that because yeah, it's known that for example, this ILW hierarchy is a reduction of KP, a reduction of KP. Yeah. So yeah, yeah. And then of course.
You remember 2 weeks ago I asked you about the interpretation. So how we can see the homological field theory from the integrable hierarchy side, so from the dynamical system?
It's I mean it's completely unclear. I mean yeah, maybe I just finish what I wanted to say. I mean, yeah, just that. Yeah, I mean, it's known that ILW is a reduction of KP. Yeah, in principle, yeah, in some other cases, it's known that DZ is a reduction of KP. Probably it's always a reduction of KP, but it's not known. Okay, and regarding your question, how to see homological field theory? Yeah, I mean, in some sense. Yeah, in rank 1, it's not maybe too interesting, but in higher ranks, it's more interesting. Yeah, I mean, homological field theory can, in some sense, it appears from genus 0. So, because if one considers, okay, in rank 1 it's trivial, but in higher rank, you know that I mean, when people consider, I mean, when if I want to consider the so-called dispersionless limit of these systems, yeah, I mean, in rank 1 it's I mean, of course trivial, TW dt equals WWX. But yeah, in general, I mean, for higher ranks, people get some systems of this sort. Alpha, beta, gamma, W, gamma, X. Yeah, where this one. Yes, for high rank. And then, I mean, if one wants to consider integrable systems of this form, when these flows commute, when these flows commute, then yeah, people in integrable systems, yeah, they naturally come to the WDV equations. Yeah, so I mean that having a solution, there is a natural way that having a solution of WDV equations, solution of WDV equations, then one can naturally get to systems, commuting systems of this sort, and to higher flows. And yeah, and then there is a famous result of Manin saying that actually solutions of WG equations are in one-to-one correspondence with homological field theories in genus 0. Of any rank, yeah, of any rank. I didn't say that, okay, the definition. But, so in some sense, yeah, I mean, there is some conceptual way to relate integrable systems, just, I mean, of hydrodynamic type of this form. In our language, we say in genus 0, to relate such systems to homological field theories in genus 0 through solutions of WDV equations. But when we speak about higher, I mean, genus, when there are terms with higher derivatives, then it's, from my point of view, it's completely mysterious, the appearance of homological field theories in all genera. it's still mysterious. So there is no conceptual explanation of that.
Such thank you.
Why? Yeah.
It was very interesting and state many interesting questions for the future research. Thank you very much.
Thanks. Thank you.
If there are no other questions, we finish here, and I wish you good evening. Bye.
Good evening. Yeah. Bye-bye.